This video is presented to you by www.testprepadda.com. Dear students, in the previous video session I started the discussion of aromatic compounds. In that session, I talked about some historical background of aromaticity. In this session, I will talk about different definitions of aromaticity. First definition. This definition says aromaticity is a property which confers great stability on compounds. These compounds undergo substitution reactions more readily than addition reactions, though they contain large number of olefinic double bonds. Now the best example is benzene C6H6. When this benzene is reacted with Br2 in CCl4, no reaction. When this benzene was reacted with H2OH plus, no reaction. When it is reacted with H2Ni, no reaction. When it is reacted with cold alkaline KMnO4, no oxidation. When it is reacted with Cl2 in presence of FeCl3, a Lewis acid, then chlorination takes place, but a substitution chlorination. My point is clear. And by this definition, this benzene is aromatic compound. Now I will talk about another definition of aromaticity. The second definition is aromaticity is associated with a closed loop of electrons with the delocalized bonding, conjugated double bonds in a cyclic ring. Again, I'll take the example benzene. This is the normal structure of benzene. You can see conjugated double bonds. Now, if I draw the orbital diagram here, delocalization of electrons like this. So, closed loop of electrons, and that is why we say that benzene is aromatic. But unfortunately, this definition does not hold good for compounds like cyclooctatetraene. I will draw the diagram. This compound, although it has alternate double bonds, conjugated double bonds, but this compound reacts with Br2 in CCl4, reacts with H2Ni, undergoes oxidation with KMnO4. So this compound cannot be considered as aromatic compound. That is why this definition fails for these types of compounds. Now I will talk about the third definition, that is from the quantum mechanical point of view. Dear students, this is the modern definition of aromaticity. Quantum mechanical model has two criteria of aromaticity. First, there should be a planar ring. Second, a loop of 4n plus 2 pi electrons which are delocalized over the entire ring. This is called Huckel's rule. Dear students, in 1931, a German scientist Huckel, he carried out a series of mathematical calculations to get a theoretical definition of aromaticity. And then he concluded that a planar monocyclic ring with 2, 6, 10, 14, in general 4n plus 2. delocalized electrons, pi electrons, should be aromatic. Now, why 4n plus 2 pi electrons? Why 4n plus 2 pi electrons? I will tell you how do we explain the stability of aromatic compounds using 4n plus 2 pi electrons. A simple method is inscribe a regular polygon corresponding to the ring of the compound inside a circle, placing a corner of the polygon at the bottom. For example, if I take benzene ring, this is the circle. Now, benzene has got 6 vertices. That is why I will put one corner of the benzene ring at the bottom. Then total 6 vertices are there. I will join these points. Now, at the points where vertices of the polygon touch the circle, we draw small horizontal lines outside that indicate the relative energies of pi molecular orbitals of the system. So this is one, this is another, this is another. So I will draw like this: one energy level, one, 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 one. So this energy level, this energy level correspond to this point, and these two correspond to these 2 points, and these two correspond to these 2 points, and this one for this. And then a dashed horizontal line is drawn halfway up the circle, dividing the bonding orbitals from anti-bonding orbitals like this. A non-bonding orbital may fall in this line. These are the bonding orbitals, bonding molecular orbitals. These are the anti-bonding molecular orbitals. The energy of anti-bonding molecular orbitals will be greater than bonding molecular orbitals. And here, non-bonding molecular orbital can fall. Now, benzene has got total how many pi electrons? 6 pi electrons. 6 pi electrons are in benzene. Lower energy orbitals are filled first. So, one orbital will get 2 electrons maximum. So, I'll give 2 electrons here. Then these two orbitals are in the same energy level. So, I'll give 1, 1. Then again 1, 1. And now you can see total 6 electrons are distributed. This was benzene. Now if I take the example of cyclooctatetraene, cyclooctatetraene formula is C8H8. This is cyclooctatetraene. I will draw the normal structure here. This is the normal structure of cyclooctatetraene. Now I will take a circle, and now one corner of this polygon I will place here, then another point, another point, another point, another point, another point, another point, another point. Total 8 vertices are present in this cyclooctatetraene. Now I will join these points like this, 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 and this. So basically, this is for cyclooctatetraene. Now, as I told you, we draw a small horizontal line for each corner. So like here, I will draw like this. For these 2 points, I will draw like this. And A dashed horizontal line is drawn to divide this into two identical parts, and then for these two points I will draw two lines, and then for this I will draw this. So these are actually anti-bonding molecular orbitals, and these are bonding molecular orbitals, and these two you can see here non-bonding molecular orbitals. Now you can see total how many pi electrons are there? 8 pi electrons are here. 8 pi electrons in cyclooctatetraene. So first lower energy orbitals will be filled. 2 electrons will be given to this bonding molecular orbital. Now these two are on the same energy level. So first 1 1, then again 1 1. So total 6 electrons, 6 pi electrons. Now here again same energy level. So I'll give 1 1. Now you can see total 8 pi electrons have been distributed. Now if you compare this benzene with cyclooctatetraene, you can easily say that in benzene all bonding molecular orbitals are filled with electrons and have their spin paired, and no electron is found in anti-bonding molecular orbital or non-bonding molecular orbital. By this way, we explain the stability of this benzene. This cyclooctatetraene has two non-bonding molecular orbital with two unpaired electrons. Typically, such molecule will be highly reactive and unstable. Planar form of this cannot gain stability. So this compound cannot be considered as aromatic. It is actually tub shape. I will draw for you. Experimentally, we have found that bonds of cyclooctatetraene are alternatively short and long. The short bond length is 1.34 angstrom and the long bond length is 1.48 angstrom. That is why we easily say that these pi electrons do not form a closed loop, and these are not delocalized. While in benzene, all CC bond lengths are equal because of delocalization. This way, we explain that benzene is aromatic while cyclooctatetraene is not an aromatic compound. If I take the benzene ring, in benzene ring, each carbon atom is sp2 hybridized. Each carbon atom is sp2 hybridized, means triangular planar. Triangular planar. So whole ring is actually a planar ring. Now here you can easily say that 6 pi electrons means it obeys Huckel rule 4n plus 2 pi electrons, and these pi electrons are delocalized over the entire ring this way. So you can say a loop of pi electrons, 4n plus 2 pi electrons, and that is why by this definition benzene is aromatic compound. Now I will talk about the fourth definition. With the advent of magnetic techniques such as NMR, nuclear magnetic response, aromaticity is defined as the ability to sustain an induced ring current. Compound with this ability is known as diatropic, means aromatic. Aromatic ring current is an effect observed in aromatic molecules such as benzene. If the magnetic field is directed perpendicular to the plane of the aromatic system, a ring current is induced in the delocalized pi electrons of aromatic ring. So this is the experimental technique to find whether a compound is aromatic or not. You can see here, this is the benzene ring. So this is the plane. Now this is the external magnetic field applied here perpendicular to the plane. This is the external magnetic field, and you can see this is the ring current. This is the direction of the ring current. Now this is the direction. This is the direction of induced. This is the direction of induced ring current. Induced magnetic field ring current. And on this basis, we predict that benzene is aromatic. So this is NMR technique of finding whether compound is aromatic or not. Dear students, aromaticity provides extra stability to the compound. Now consider a compound here, Cyclo Butadiene. In this compound, you can see 4 pi electrons. There is a loop of 4 pi electrons. This does not follow Huckel rule. This does not follow Huckel rule. So this cannot be the aromatic. This is not the aromatic compound. So this compound will be less stable than aromatic compound. But because of this conjugation, we expected this compound more or as stable as non-aromatic compound. But experimentally, this compound was found to be much less stable than aromatic as well as non-aromatic compound. And such type of compounds we call anti-aromatic compound. Anti-aromatic compound. Definition of anti-aromaticity is: an anti-aromatic compound is defined as a compound that is destabilized by a closed loop of pi electrons. And let me tell you, the condition for anti-aromaticity is a planar ring, and a closed loop of 4 and pi electrons. This is for anti-aromaticity. You can see here, each carbon is sp2 hybridized. So this is a planar ring. Second thing, 4 pi electrons means this compound is anti-aromatic. And students, let me tell you, because of their instability, these compounds cannot be isolated under normal conditions. Dear students, in the next video lecture also, I will continue the discussion of aromatic, anti-aromatic and non-aromatic compounds. Thank you. This video is presented to you by www.testprepadda.com. testprepadda.com provides free audio-visual lectures of different subjects by expert faculties, free online tests prepared by expert faculties to students who are preparing for engineering or medical entrance exams or planning to take exams like KVPY, Olympiad, etc. It provides a platform where students can interact with mentors to improve their performance in the exams. The mission of this online medium is to help students to achieve their goals. Log on to www.testprepadda.com to watch free video lectures on different topics, to download free revision notes,
to take free chapter-wise online tests, progressive test, and mock test, to discuss doubts with mentors. Thank you for watching the video. To stay up to date with the latest videos, subscribe to our YouTube channel. Like us on our Facebook page, Test Prep Adda. All the best.